Good morning. I wanted that, that we start with geometry and then the combinatorics, the genre, from the problem where we left it. Um, I'm going to introduce geometry. 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 Yes. I'm assuming you all know geometry. We're going to start with some basic techniques to consider when solving geometry problems. The first one I'm going to give is draw a diagram to visualize the problem. That's the first technique to consider, drawing a diagram. The second one will be drawing a deliberately incorrect diagram. Deliberately draw an incorrect diagram. To avoid accidentally assuming the result. Because of reference to an accurate diagram. I think this number 2 is particularly important because one of the things you will notice is when someone is solving the geometry problem, maybe the question is that show that some three lines are concurrent. So you would see something like this. Supposing we have a triangle. Let's call this point A, B, C. Let's call this point K. And so we have a line through K, the bisector of AB. And then we also, supposing you also have another line here. And then we have, let's consider the X circle of this. And we have a line from the X center. And maybe the question is, show that IA and this point, that IA passes through this point. Show that these three lines, essentially this line L1, L2, and L3 are concurrent. So one of the first mistakes you see someone making is when they draw this accurate diagram where those lines are concurrent, it is much easier to make relationships between angles because most of the time you can easily relate angles that are formed by these lines to each other. So you'll find someone using arguments of those angles to prove concurrency. So the only issue that you get there is the angles in question, the relationships you found. Let's say you found that this angle is equal to the angle. The only issue you get there is the assumption you've made is that the lines are already concurrent. And that is what you're supposed to prove. So the dangers of accurate diagrams is you can use the result to prove the result. So that's why you want sometimes to draw an inaccurate diagram so that you don't try using the result to prove the very same result. The next that we're going to go through. So number 3 is try to relate as many angles and line segments as you can. Try to relate as many angles and line segments as you can. It's always the best way of starting geometry problems. When you don't know how to start, just find which angles are related, which lines are related, and what is the relationship. And after you build the relationship, use that to construct your problem. Number 4, you can do this. You can assume that the result is true and see what follows. But always keep this in mind. Every time you're assuming the result is true, it's an assumption. Do not commit to it if it's an assumption. So assume the result is true. And see what follows. Okay, I don't know, the example I want to use for this is a problem I gave you yesterday. That is CSI mock question 4. Let me just highlight it. So in the question, we have points A, B, and C, and we are told that we have an in circle, and we have points. We have point K, point X, and Y, such that the line that tangent to the in circle passing through X is parallel to AC, and also the line tangent to the in circle passing through Y is parallel to AB. We also have the other condition of AB is less than BC is less than AC. I think this is the condition. And so, again, you're told that the second circle of this triangle, we have another point that this line crosses, and that point is the point P of a gene. And so what you're told essentially is to prove that X, P, Y plus, there are other points defined here. The midpoint of AC, point L, and the midpoint of AB, point K. And they come to the in center there. So you're told that prove that angle KIL is equals to angle XPY. Where, let me use another proof. But this is X, Y, and this is P. So prove that these two angles, no, this is not what. KIL plus angle XPY is equals to 180 degrees. That's the problem statement. So one thing you can do, even before you start solving, is assume that the two angles, this angle plus this angle, they add up to 180. And one of the things you'll notice immediately, I won't solve this problem. I gave it to you guys, so you won't solve it. But one of the first things you notice is that if I'm to assume that this angle is add up to 180, one of the things I can do is essentially observe that this is a parallel line, this is also a parallel line. So I can apply number 3, relating angles. I can say that this angle is equals to this angle, right? I can also say that, let me call it more later. I can also say that, which other angle can I relate? There are many angles I can relate here. Let me call this B is equals to this angle here, B. They also have AB also have this angle, alpha. And this angle is also B here, this is also A. So this is also angle alpha. And keep something in mind that this line, the line AP, it passes through the in center onto P, but then this line is tangent to the circle and also tangent to the circle. So because they're tangent to the circle, it means if you have two circles, you have a circle and you have two lines tangent to the circle, then it means this is equal to that, right? And if I'm to draw a line from the in center, this angle would bisect that other angle. For that reason, we'd have this angle here being equal to, we'd have two things. One, that these lines, this line here, and this other line, that is the line, okay, let me name it R. The line R that passes through X, and the line Z that passes through Y, they meet at some point T, but also line AP meets at that point T. So that will be this point T. We are here, and we have here's X, here's Y. Yeah, something like that. So we can relate that angle. Another thing we can do is we can say, let me draw a line there to this point T. Let me draw another line to that point T. And so I ask, which other angle can I relate? I'm not seeing them. Which other angle can I relate? Let's do this exercise. Try finding an angle I can relate, or any segment I can relate to the angle. Anyone seeing anything? There's still many things I can. No one has seen anything? Okay, let me show you something. What if I come and draw this line? I come and draw the line from B to P and the line from P to C. Yes. Is there anything visible, sir? Anyone seeing anything? That line? Okay, I see no one seeing anything. Tanwi, what is it? Okay, so there's something maybe I'm seeing. I'm seeing that I have code AC, and this code AC, it is subtending an angle APC. But I'm saying that this angle APC is the same as angle ABC, right? So I'm seeing that relation. Anyone not seeing that? Okay, anyone seeing that? Okay. So I have angle APC is equals to angle ABC. So let me call it some small a. Although keep this in mind when you're writing your solution, you don't do this. The examiner is not interested in it. It's good to write them when you're doing angle chasing to keep track of the angles. So what you're doing is called angle chasing. You're saying which segments are related to which segments, which lines are related. So okay, so we are noticing APC is equals to ABC. Is there anything else you can observe? I believe there's something else. Anyone seeing anything? Honestly? What else can you observe? Let me see. That's Brenda. Brenda? Okay, I see. Well, I'm seeing something. I'm seeing that this is A, and this is A. But then I'm also seeing here I have A. So it means angle TYC is equals to 180 minus A, right? Okay. So if angle TYC is equals to 180 minus A, and angle TPC is equals to A, that means I have a quadrilateral such that TPC is A and TYC is 180 minus A. Well, anyone else tell me what is about this? Someone, anyone? A quadrilateral where the opposite angles are supplementary. How many are going to have? Precisely. Precisely. So that means I have a circle here. Okay. So that's another relationship. And should that be important? Maybe, maybe not. But the interesting thing about cyclic quadrilaterals, about circles that you want, is that I know if I draw lines there, then this angle is equal to this angle, right? So with circles, I can relate more angles. So what I'm going to do is I'm going to look at this diagram and say, okay, they are cyclic. It means this angle here is equal to which angle? Angle APY is equal to which angle? Hey, Benyamaz. You're too quiet. You're too quiet. AP. Okay, so I have a circle. I have a circle PTYC. With that circle, angle APY should be equal to each other. Done. Let me get something from here. Okay, take a minute. Take a minute. Take a minute to look at it. Let me clarify. Point T is here. This point of concurrence between this one. Yes, that's point T. Okay, so that's that. Mhm. Let's go back to number one. Draw a diagram. Okay. Draw a diagram and visualize that. And convince yourself what language is the best to one another. think I should also redraw the diagram. Maybe we can make it clearer. Let me redraw the diagram. So, if I show the diagram and do this. We can draw the diagram and how I have triangle ABC. I have triangle ABC. And the problem says that there is an incircle into the triangle. And it says that there is a point on BC that is not C, such that there's a point X on BC, such that the line tangent to the incircle, a line from through X, tangent to the incircle, is parallel to AC. Okay? We have that. But then there is also that there's a point Y that is not B, such that the line tangent to the incircle is parallel to AB. So I have a line tangent to the incircle through Y that should be parallel to AB. Okay. So what is going on? I have an incenter here, incenter I. Okay. Now, I also found that, so I can draw a line from A through I and it will pass through X. I hope we can all agree on that. Sorry, we can draw a line from A through I and it will pass through the point of intersection of these two lines. Okay. And I also have that the line AI will meet the circumcircle of ABC again at point P. So I can just draw the circumcircle ABC and denote this as point P. This is an intersection point. Okay. That's my new diagram. Okay. And so what is left for me is essentially to do angle testing. Find which angles relate to which angles and which lines relate to which lines. Alvin? Mm-hmm. How you show that? What's the okay, this is that. So notice, okay, so notice in the incircle, AB is tangent to the incircle, right? And you also have AC is tangent to the incircle. And the line X is also tangent to the incircle, and Y also tangent. So let's just draw that separately. So we have a circle, and we have point A. Let me call this point M. Let's call this tangent point N. Then I also have a tangent point here. Let me call it a letter. Give me a letter. K. Okay. K. Another letter. L. Okay. So I have the center here. I can just draw that. And I know this angle is 90 degrees, right? Also know this is 90 degrees. I know this is 90, I know this is 90. I also know that because AM is tangent to the circle and AN is tangent to the circle, I have that this is equal to that. That's correct, right? And I also have that this should be equal to that. Is that correct? Okay. So here, supposing, let me call this point a letter Q. Let's call this point Q. So I want to draw a line to the center of the circle. Is there anything interesting about these two triangles, QKI and INQ, that you can observe? Anything about them? There's something about QKI that you can say about triangle QKI and triangle INQ. Anyone wants to help me? Who wants to help me? Mhm. Okay. Right. Yeah. Yeah. Mhm. Exactly. So that's exactly it. Very well put. So KQ is equal to LQ. We have KI and IL as both the radius, so they're also equal. The tangent is common, so it's also equal. So we have that the two triangles IKQ and ILQ are similar. So because they're similar, this angle here is equal to that angle, right? That angle has been bisected. What else can you observe? Um, okay, so we can also make the same argument. So let's draw deliberately, draw a wrong line there. Let's draw a line that comes to that center. We also have this angle is equal to that angle. Okay, so there's nothing that can tell us that AI and AQ are collinear. There's nothing that can tell us that. But then there's a condition from the question, and that is that KQ should be parallel to each line. Mhm. So when there's a condition from the statement, there are some parallel lines you were dealing with here. So KQ should be parallel to each line. I want this to come from you. Come from who? Um, John, yeah. Uh-huh. To AC. Yes. And yes, to AC. Okay, so we had yeah, parallel to AC. And so this is our AC. Okay. So our AC is tangent to the circle. So we have this angle line is parallel to this line. Okay. We had another condition for another set of lines that are parallel to each other. Someone wants to help me identify them. Which other lines are parallel to each other? Maybe it's Ronald. Ronald? Which lines were parallel? Which other set of lines are parallel? KQN. Okay, I think you already said KQ parallel to AN. There's another set of lines parallel to each other. Yeah, AM and QN, precisely. So yeah, these are also parallel to each other. And so let me and so essentially, okay, the diagram looks very, it doesn't seem to show parallelism, but once these lines are parallel to each other, we can just redraw it. We cannot just redraw it. And you're going to have something like this. You're going to have two lines that are parallel to each other, and then two lines that are parallel to each other. Parallel to each other. And then they have a common circle inside. So they have a common circle inside, and they're all parallel. So because they are parallel to each other, if I were to, so if I have this is the center of the circle, I come and create an angle there. Okay. And I also come and create another angle there. These two angles are going to be, are essentially going to be equal. I don't know, can you see? Can you see it now? Can anyone see that these two angles are going to be equal? Can anyone help me confirm that? Could you help me understand one? Right? Confirm? Mhm. Okay, so again, you now want to be cautious. What you're trying to show is that this line here, what you're trying to show is that the line AI what you're trying to show is that this line here, it's a straight line. So we can't use it proving that. So we can't say that the create a Z angle because now we're using the results to try proving it. Right? So that's again why you don't want accurate diagrams. It doesn't happen. So I've deliberately drawn it wrong, but there's something we can see. The something we can see is that this line is parallel to this line. And then there's a common line here. So it means this angle here is equal to that angle. Is equal to that angle there. Okay? But then this angle here, which is equal to this angle, because this line is parallel to that other line, it means this angle is also equal to this. So I can have angle alpha, angle alpha, angle alpha, right? So essentially have these angles that are equal to each other. And then I also have these other angles, let me call them better, that are going to end up being equal to each other. And then I fit in a circle in this parallelogram. I fit in, is it a parallelogram? Yeah, it's a parallelogram. I fit in a circle in this parallelogram. So if I don't know how to parallelogram, I fit in a circle. Okay, there will be some conditions for the correlation side, but I fit in a circle inside there. If I'm going to have a center, what is going to happen is the parallelogram. I know that if the line, I draw a line from here to the end, I know that this angle, alpha over 2, must be equal to this angle, alpha over 2. Right? Right? They still don't see that? I repeat. How many will only you? How many are saying that? Okay, nice. But then again, I have that this line to the center, so we got that from here. And this is so you also have here that this should be alpha over 2, and this should be alpha over 2. So those angles are equal, right? So now that they are equal, now it enforces what you say, the transversal. So it has to be that this angle here is essentially a straight line. It has to be that a straight line because the only way I'm going to have this angle and this angle equal and have that set of parallel lines is if and only if it's a transversal, a straight line. So this angle is equal to that angle, and this angle here in any parallelogram, and I must have that. So that's precisely why I say AI and that line is what? That line is a straight line. This AIQ, that line AIQ is a straight line. Or I can say points AI and Q are linear. Okay, it does. Okay, you can highlight, but the question is to show that. So again, we want to go back to the question. Show that angle XPY is equal to angle KIL. Let me draw KIL. But I want to be cautious when drawing because I can come and put K upper and L upper, but then that's a problem because K and L are the midpoints of AC and BC. They don't necessarily have to be the tangent points of the in circle. So I'll deliberately put K here so that I don't forget that and put L here. And then I draw this. So the question is, prove that this angle plus this angle add up to 180 degrees. So I want to go back to the question. Yes, this is important. This is an interesting observation. It helps us. But then again, we don't want to focus too much on this. It's not part of the solution. Our solution is anything that can help us show that KIL and XPY add up to 180. So remember what we said yesterday. The whole idea is when you're writing your argument, you must always invoke why exactly are we making this statement? What condition on the problem that we obey. Because if you don't obey the conditions on the problem statement, you've set your own question. So if you come and write this, and we get too obsessed with this, the examiner will say, nobody asked you to show that this is alcohol. So you've essentially set your own proof. You can only use it as a step showing your proof. That's why I didn't spend so much time on it. I just said that we know that this line is straight. We didn't spend too much time. And the reason I use it, it's not fun. It's good to highlight why exactly you're saying the line points out. Yeah. But don't spend too much time on anything that doesn't help you relate this angle to this angle, because that's the question. Okay. So I don't know if I answered the question now. Okay. Any other question? Okay. Back to our angle chasing. Okay, I don't want to do it, so I want someone to come and help me do angle chasing. That's a forgotten. We're going down. Yeah. Yeah. Let's try and as we pray, let me give the last two rules I had to give. And then we can finish with it. Okay. Let me try the last two techniques. Always check. That was the last one was which number? 4. So this is 5. We're going to number 5. So always check that you have considered all cases. All cases. And number 6, finally, don't be afraid. Okay, if you have the knowledge, it will be easier. But don't be afraid to get your hands dirty. With trigonometry. Although this might need some practice knowing how to work with trigonometry. So you can use trigonometry to relate lines and to relate other angles. Coordinate geometry. So coordinate geometry is, for example, there's a question on a circle that Dr. Humphrey did yesterday. The solution she presented was on coordinate geometry, on working with the midpoints and working with vectors. Coordinate geometry and or algebra. There are some algebraic techniques very common in geometry. One of them is called the triangle inequality, where the triangle inequality says if you have a triangle, let me push this up. The triangle inequality says if you have a triangle A, B, C, then AB plus AC. So supposing AB is less than AC, which is less than BC, then AB plus AC will always be greater than BC. That is, you cannot have a triangle where one side is bigger than the other. They can't ever have. There's also something interesting, an algebraic equation, very popular in geometry, we call it the Pythagoras theorem. And Pythagoras theorem says, someone tell me, what does Pythagoras theorem say? The guy. Mhm. 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 Yes. Aha. Okay. Also, before we listen, what is the relationship between we have some, I know that 3, 4, 5 is a Pythagorean triple, right? 3, 4, 5. So what is the general relationship between I'm looking for general form. For all numbers 3, 4, 5, there is a 8, 12, 13. 8, 8, 16. 8, 15, 16, and 17. I hope, is this correct? 8, 15, 17. Okay. Another one, for example. 24, 26, 10, but I don't 10. So 10, 24, 26. Yes, so these are Pythagorean triples. We know they'll satisfy. So my question is, how can I generalize for all real numbers and all Pythagorean triples? Anyone knows how I can do that? Okay, I'll leave that to you, but the generalization is this. I take some constant k, I multiply it by some u squared minus v squared. That will be the first triple, the smallest triple. And then I take k, the constant k, times uv. So k is for the multiples. So all multiples of 3, 4, 5 are Pythagorean triples. So these ones, the lowest forms of the Pythagorean triples, we call them primitive Pythagorean triples. Call them primitive Pythagorean triples. And they are u squared minus v squared, uv, and then u squared plus v squared. So you can convince yourself that these expressions will always satisfy the Pythagoras theorem. You can convince yourself that you can just come and plug them. Base, you can come and square this plus square this is equal to this square. It will hold. So if I generalize on all real numbers, on all integers, that is, I'm going to have here k times u squared plus v squared. So our Pythagoras theorem and the triangle inequality are going to appear many times. It will appear in algebra. It will also appear in geometry. Pythagoras theorem, very later in the triangle inequality. The sum of two sides is always greater than the largest side. Yes, the question. Which will be 2u times 2uv. Sure. 2uv. Okay, that's how we will write it. Write 2k and uv, or here 2uv. Thanks for that. Otherwise, it's okay. In another issue. Okay, so that's Pythagorean triples as the triangle inequality. Any questions? Anything not understood? Anything understood? Maybe that's a better of asking it. Anything understood? Yes, that is so how many are still writing? Which question? Can I scroll? Can I scroll now? So let me come back. As I said, I want to be solving this problem because I gave it to people to fight with first. So I'll solve it later in the day. But one heuristic I want you to go try to okay. I'll give you a hint. The most important hint in solving this problem. Relate as many angles as you can. If you relate as many angles as you can, you will find that because this line and this line are parallel, this and this are parallel, this angle should be equal to that angle. Let's call it B. And this angle, let's call it A, should be equal to this angle. Let's call it A. Again, you're going to find that. And you'll also find that we can also say that this angle, let's call it alpha, is equal to this angle, let's call it alpha. Just relating the angles to each other. What else can we find? We are going to also find that this angle, as you've shown hapa chini, is also alpha, and this one is also alpha. But one thing you must always know, don't get too excited. Because if you get too excited with the angles you're finding, you may focus on the wrong thing. One thing that tempted me, I remember having that temptation, I was looking at this problem yesterday. I had this strong temptation, but what if this angle and this angle, there's something special going on? There's nothing special going on. There's just angles that are equal. It doesn't, the equality of this angle and this angle doesn't help us solving the problem. So if you get too excited with such patterns, you may spend so much time following a path that doesn't help solve the problem. So you must also be clear on drawing your plan. I hope you can remember from the last camp, we talked about problem-solving strategies by Olympiad. That is, the first step is always, after understanding the question, craft a plan. And one of the best ways of crafting a plan is rephrase the question. So I'm going to rephrase the question right now. How am I going to rephrase the question? I'm going to look for more angles and lines that relate to each other. And I'm going to say, if I were to draw that BP and PC, just drawing the segments so that I can relate them, I have that angle APC is equals to angle ABC. So this angle is A. I have that angle is A. I also have this angle here. This angle here is A. This one is also A. So I have that this angle is 180 minus A. Essentially, I have found for myself a quadrilateral such that I have 180 minus A, I have A, such that the opposite sides are supplementary. So I've gotten a cyclic quadrilateral. Is that important? Well, let's see. I have a cyclic quadrilateral. I can make the same argument for quadrilateral PBXT. So I can also find another cyclic quadrilateral here. Okay, so if I have this cyclic quadrilateral, what does it help me with? It shows me that angle, so this angle, that in this chord here, angle TY, the chord TY extends angle TPY, but again, it extends angle TCY. So this angle is equal to that. The other thing it tells me is that angle, the chord TX, let me use a different color. The chord TX extends angle TPX, this angle, which should also be equal to this other angle, TBX. Okay. So, why is that important? I've shifted the perspective, changed my perspective. So I'm trying to reflect. I don't want to ask myself what the examiner is asking me, that KIL plus XPY is equals to 180, because I don't know how to show this. But I want to say, can I find other angles that are related to this that can help me create this relationship? So I have that KIL, convince yourself of this later. I have that KIL, angle K, sorry, not KIL. I have that angle XPY. XPY is equals to angle XPY is equals to angle TPY plus angle TPX. But then Because of the circles I have found, I also have that angle TPY is equals to angle TCY. So this is equals to angle, is it? Okay. This is equals to angle TCY plus angle TBX. Okay. So I've found different angles to relate this relationship. So what exactly does it remain? I need to find some angle, let me call it angle delta, such that if I add angle delta to angle XPY is equals to 180 degrees, if I can find, then I say, if I can find an angle delta, that if I add it to XPY is equals to 180, and then I can just say, can I show that angle delta is actually equal to angle KIL? So that's how I've restructured the question. So I will come back to this triangle. I'll go to triangle. I'll go to triangle BTC, sorry. Then I'll say, I have this angle and I have this angle. No, they're not equal angles. I have those two angles, and one of them is angle TCY. So I have angle TCY, and the other is TCX and angle TCY. So I can say, because the angles in a triangle add up to 180 degrees, I can say that this angle here, let's call it delta. I can say that 180 degrees, the sum of angles of the triangle, is equals to angle TCX plus angle TCY plus some angle delta. Okay? But then the problem is to show that TCX plus TCY plus KIL is equals to 180 degrees. So I can reconstruct the problem and say, the problem statement is analogous to showing that my angle delta is equal, that my angle delta is equals to KIL, angle KIL. But angle delta in this triangle BTC is essentially which angle? Which angle is it? Who can identify the letters of that angle? Therefore, now not alone. Okay, so the angle of the index. So angle BTC, so I have angle BTC. So essentially, I've written many things, but okay, let me come hopefully instead. I've written many things, but essentially, the problem statement can be restructured as show that angle B. Okay, so let me not write show that. So if you're writing your answer, you can word yourself like this. You can say the problem statement is analogous to showing that angle BTC is equals to angle KIL. Or another way you can word it, you can say that it suffices to show that angle BTC is equals to angle KIL. Another way you can reword it, you can choose which way you want to word it. You can also say that if we can show that angle BTC is equals to angle KIL, we will be done. Essentially, if you can show that angle BTC is equals to angle KIL. So what I've done there is I've gone from the difficult problem statement of angle KIL and angle XPY to considering the simpler problem, that is the angles in a triangle. Then I'll say that let's prove this instead of what you were asked. Why exactly? Because now this is analogous to what you were asked. So that way, I've simplified what I need to solve. Yeah. How many on my how many how I did so okay, what was this letter? Try reconstructing this step until you get to this problem. And then from here, your task is now to complete the solution. Come and show that angle BTC is equals to angle KIM. And follow the rules we've given them. The rules are these. Draw a diagram to visualize the problem. Sometimes deliberately draw an incorrect diagram to avoid accidentally assuming the result because of reference to an accurate diagram. Try to relate as many angles and line segments as you can. Sometimes you can try assuming the result is true and see what follows. See if you can see something if you assume that the result is true. Because sometimes I remember, okay, sometimes it can be really hard to know where to start. Okay. But you can assume that the result is true, you get a so, for example, for me, when solving this problem, what I assumed, the first thing that I assumed that helped me see what I was doing was I assumed that we have the insider here. So I assumed that AI, that let me reflect AI on this other side so that I have some point here. Let's call it A prime, so that this is equal to that. Why did I assume that? Because if I can assume that this line, this is equal to that, I also have that K is here and L is here. And it means this line is equal to this line. Because K and L were the midpoints of the segments AB and AC respectively. So if I can assume that AI is equal to IA prime, then I'll be forced, if I connect this here, and I connect this here, I'll be forced with the realization that this angle, this triangle here, AKI, is similar to is it congruent, right? It's congruent to AB A prime. So it has to be that this here is parallel to this. And it also has to be that this here is parallel to this. Is that correct in the context of our problem? It's wrong. It's very wrong. That's why I didn't include it in the solution. It was an assumption I made to help me try seeing what do I need to do. And so once I did this, I'd find that because now I have this line here parallel to this, it means this angle is equal to that angle, and it means this angle is equal to that angle. And essentially, I've already seen what we were doing here, BTC. So essentially, I can say that I can actually run away from KIL by finding some point T such that BTC is equal to KIL. So that is what motivated me to start doing angle chasing to look for relating B to the smaller angle XY. Because if I can relate BTC to some XPY hypertonic, then I've found a leeway for restructuring the problem statement. Yes. So sometimes you want to assume some results and see what is general. Just keep it careful. And then after you make the assumption, make sure your assumption is not false. That's the assumption I've made. There's no reason why this AI should be equal to IT. There's no reason why they should be equal. I just assume that to help me know how to start. Okay, so that is that. Any question on that? Any genuine question? You have a question? You can't exactly. And one of the ways you can see is try drawing smaller things. Try drawing 3. by doing a rectangle, by doing a pentagon, and try seeing the property in the comment section. So then you hold it, because if you have a regular endpoint, so if it's a pentagon, if it's regular, what does regular mean exactly? Nice. So it means for triangles, we have an equilateral triangle, and that's very beautiful. The properties of the equilateral triangle are very few. If it's quadrilateral, we only have the square. If it's pentagon, we have a regular pentagon. So you want to draw small quadrilaterals and see the condition being given. So I'm assuming it's geometry and not combinatorial. So we have some combinatorial platform. We also have number theory problem. But if it's geometry, we just want to draw small quadrilateral, or small pentagon, small polygons, and see the condition has been given. Does it hold for these small cases? If it holds for the five cases, you're going to find a relationship between some of the angles. You're going to find a relationship between one angle and, let's say, the sum of all the angles, or the sum of the exterior angles, or something like that. So you want to find as many angles in that relationship. And if you can find that in a triangle, in a square, in a pentagon, in a hexagon, if you can find that in a hexagon, then you have a starting point. You can come up with the hypothesis. You can say conjecture, this is my conjecture. And then this is the proof and things. And then you can start crafting your proof based on those small things. So essentially, the best strategy is consider small things if you have a regular. Because most of the time, it's a pattern that is repeating to you. That's what they usually have. Yeah, any other question? Okay, so that is an introduction to the okay, I need something. How many things? We don't proceed. Okay, let us proceed to the next one. So the tool, there's a question. Yeah. How should one write their geometry solution? The proof. How are you going to structure it? To write your proof, again, I'm going to. There are two ways you can write your proof. The best way is come with a claim, what I did yesterday, claim or conjecture. Make your claim there, and then come and say proof. Then make your proof underneath it, and then come and state the claim. State claim. But then, if you're not sure of the claim, or you don't know how to write that this is the claim, you can do this as well. This is also preferred, although it's harder to be. You need a lot of practice to be accurate with the method. But in the second method, just bring your proof or argument. Just bring the proof, and then after the proof, state claim. State that from our argument we found that this is. Why exactly do I not like this one? Because I don't like it. You go to the contest, and you write your proof, and you make the whole thing becomes false. And this was a mistake one of Tony did in the IMO problem one. He found the solution, but Sasa his argument was wrong. So what the examiner said, the solution was correct, the argument was wrong. Question: how did the claim follow from the argument if the argument was wrong? So everything was wrong from top to bottom. So that's the disadvantage of this proof of starting with the argument, then stating the claim. But if you state the claim first, if you found your claim, if you state it first, and it's correct, you'll get, and the first part of your proof is correct-ish, it's heading towards this claim, then you can give your one. And this is, I believe, what Gilbert did in the PAMO, the functional equations. Just said, These are the solutions. And then this is how we found them. And then the others, if you didn't complete the proof, but you just found the first few solutions, claimed them, and so you're given a point for that. You claim the solution and say, okay, this is how we found some of these solutions. I can't complete the proof, but I've given you the claim. And so, because the answers you gave were all the answers that this, so you get 1 point for that. So I really don't usually like this. You can do this if you don't know how to claim, if you don't know what to claim. Sometimes you can make incomplete claims. Like we had Cynthia Moria. She made, there were, I think, 3 answers in the function. She claimed only one of them. And because she only claimed one of the answers, the examiners are not going to give you a point for that. It doesn't matter what you do. Because in functional equations, you want all of them. You want all of them. So supposing you don't know what to do, if you don't know what to claim, you can come do your proof argument and then state your claim. But then again, it remains risky because the proof and the argument is usually very tricky. So if you don't know or you're not sure of how to put your argument in your proof, just say this is what I think. Maybe you can do trial and error. Actually, this is the best way. Do trial and error and then find answers for the thing. Like Adikama, you don't know how to answer. Come and say, these are my answers. And this is the format actually. You usually say the answer is this. After saying the answer is this, you say proof for the answer. And then it's analysis. So what you want to say is, I found an answer by trial and error, but I want to get up. I know I can't craft a good proof for this, but I want to at least get a mark. So come and put your claim, and then try crafting your proof. Even if the proof is crafted, you stand a better chance at getting points than if you use the second presenting your answer. Okay, so that is the general way of presenting your answers. So how about geometry? Geometry, where we've asked you to show that an angle is equal to another. What will your claim be? Will your claim be that angle and angle, this other angle are equal? That can't be your claim because that's the question. So geometry becomes slightly different. In geometry, what we do is you come and say, you just jump right straight to the proof. The first thing we do, if you have used any special angles that we don't know, let's say you don't want to keep writing angle KIL, you want to denote it by some letter alpha, you come and say, first of all, you come and define, stroke declare notation. So you want to say, if you want to use alpha, you say, let alpha denote angle KIL. Let beta denote this other angle. Especially when you want to work with the coordinate geometry or trigonometry, it's very hard to just write angle KIL. It's usually much more intuitive if you just write alpha. So imagine you want to do Pythagoras theorem, and instead of saying base squared plus height squared is equal to hypotenuse squared, you say that angle KIL squared plus angle KBT, let's say, squared is equal to some angle BKD squared. Let's just assume that. So this becomes more hectic to write. So most people prefer going back to letters. But if you go to letters, we don't know what they are. Even if I know what you're saying, I'll pretend that I don't know what you're saying. You want to, first of all, define and declare notation. After you've defined and declared notation, let this angle be this, let this angle be this, let this angle be this. After that, you want to, if you've done angle chasing, there's a section here now for angle chasing. Highlight angle chasing or highlight relationships. So highlight relationships. So you don't have to, so in geometry, you don't have to say definition of notation, or you don't necessarily have to write these as subtopics. You just say, just have a small section where you're defining things, and then have a small section where you are doing your angle chasing. You're saying angle alpha is equals to 180 minus angle beta. You're just showing the relationships that you form from your angle chasing. For For example, for me, what was useful here, in that previous problem, was that I can find a way of showing that PTYC is cocyclic by relating some angles. So all I need to do here is show which angles they relate with each other and how did they relate with each other. So after I've said the relationships, this angle is equal to this other angle, this chord relates to this other chord in some way. After I've said those, now I want to say, how does this help me craft my proof? I want to say, since alpha is equal to 180 minus beta, we have that quadrilateral PTX BD is cocyclic. So now I want to start naming the result of the relationships I've seen. And I want to show now how it builds up to my solution. So essentially, now I want to do the proof, the so-called proving. And then after I found my solution, I end it. I just, first of all, when I end, I say, I restate the claim. I restate the problem statement. I restate the problem statement, the claim from the problem statement. I say that, therefore, angle KIL is plus angle, that's the angle, is equal to 1. I say, therefore, whatever we are supposed to prove is true or is false. Therefore, or I can say by contradiction, we have that claim is the true or false. Something like that. You want to restate the problem statement after the proof. So in the proof part, we are using the relationships to say, okay, we made these relationships. Why are they important? They're important because relationships from A tells us something about B. The question is asking us about G, but the relationship A and B is telling us something about C, which tells us about B, and we know that it can be C directly to G. So we can use those relationships to restructure a problem statement, to work around with the angle until we find a solution. So in the proof section, we're just saying, we observed this angle is equal to this angle. We observed this chord is maybe concise, is concurrent to this other chord. Therefore, they tell us this about this other angle, which leads to this, and eventually to the problem statement. So that's a rough view of how you want to structure your proof. And in geometry, when you're writing, when you want to highlight relationships of the proof, you always want to have, let's say you want to say an angle, you want to block it, you want to create a block for your solution. So this is what I mean by a block. Give me a statement like we observe that this of this, or it suffices to show that this angle is equal to this angle. But then when I'm showing the angles, I can say, so this is your page. So I'm going to say something like angle AIM. Okay, let me not use KIM. Let me just use arbitrary letter. Angle ABC is equal to the angle XTY plus angle YZT, which is equal to something, something, which is equal to something, something, which let's say implies that arc ABC plus arc ACB is equal to arc KLM. So I've created something like a box, something like a module here, so that I have some space. Imagine I have some space here. It's like some form of indentation. Just keep my work neat. So you want to be able to present it in such a modular form. It's very important because if you throw everything everywhere, we can't exactly read it. And also, it's not an if. You don't want to give me English. You don't want to tell me angle ABC. There's some solutions I've seen. You find someone Amandika angle, instead of this symbol, they've said angle ABC is equal to, instead of writing this, they've said is equal to angle this, equal to angle this. At the end of the day, you have a document. It's just words, 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 words. And it's very hard to read, very hard to mark. And most of the time, if you're using the reason mathematics is developed is it's very rigid. If you give me English or some other language, it's likely you're going to start contradicting yourself or something. So there are two problems. First of all, you can't to back, you can't to me. Second, you're more likely to contradict yourself. So just use symbols. Don't say we have that at KLM. Don't say we have that at KLM is equal to this other arc. Just say KLM equals to something. Therefore, this other one equals to something. Short and terse and clear. I'll understand what this means. I'll understand. And also don't jumble everything together. Siseme at KLM ukishamaliza tena may squeeze something else, may squeeze. So you want to have kind spacing. But let's say after that you want to now make a general statement. Then you can come and start with general statement, make it here, and then say what results does it tell us from a similar terms of angle ABC is equals to angle GKE. That's it. And then you can end your proof with something. So you want to structure your proof even. How about the diagram? How about the diagram? Are we supposed to go the okay, we don't care about it. We don't think that. But then when you do PAMO, when you do IMO, you'll be given the option of submitting your answer. So maybe you gave me a lot of English and you confused me somewhere, so you don't know what you mean. And that's why you have team leaders. You know, American examiners, and they're saying this is what Kevin. So this is what Kevin was trying to say. This is what Kevin was trying to say. The only problem is sometimes I think it doesn't know what he was trying to say. So there's nothing he's defending exactly. But his work is to try saying, I know he's written something we can't read, but this is what he was trying to say. This is what he was trying to say. Most of the time, they'll just give you a zero if they can't understand what you're trying to say, or if they find contradiction. So they always say you have the option of submitting rough work so that we look at the rough and understand the most of the time. And so in your rough work, that's where we're going to have your diagrams and everything. So your rough work, mostly the diagram, just draw it in the rough work. But if you're not sure of your proof, you don't know how to structure the proof, to machine work, to construct a good proof, you can just put a diagram there. It's not advisable, but if push comes to shove, just do whatever you need. Just do whatever you can. And another mistake you cannot do is if you have a diagram and you've named angles, maybe this angle is equal to this other angle. Never assume that the examiner is going to look at your diagram. Never assume that I'm going to come and say, if in the proof you come and say that angle A, B, I, C, D. If you come and tell me alpha is equals to, sorry, that's no, that's angle ABI is equals to alpha, which is equals to angle ICD. Therefore, angle ABI is equals to angle ICD. I'll look at it and then I'll say, I don't know what alpha is. So that's why you want to define your notation. You want to say, let alpha be this. But even if you have a very clear diagram alongside that I can see, I will not care about the diagram. My work is not. So I'll just ignore this, say, I don't know what alpha is, and therefore you're lying to me, and the whole thing should be wrong, even if it's correct. So if you're going to use letters that are not in the problem, this is this. Let alpha be this angle. Let beta be this angle. So those are just some things. Any questions? Yes. So you can and you want to use the name of So if I knew the name, I could say, like, let's say by Pythagoras theorem, this and this, right? One thing you can just do, and you can write something like, if you're sure, it's a theorem, and just say, you can come and write, like, let's say you're writing your proof, then utakuja tu andika small subtitle theorem. You can write THM, you can just write theorem in full. Then you're going to say, you're going to claim the theorem. All xi at this and this angle is equal to this angle, this is equal to this angle, and then you make a proof. You don't have to tell me which theorem it is. Just write that it's a theorem. So when I look at it, if I don't know which theorem it is, that's my fault as well. Because if it's a theorem, every mathematician should know it. Theorems are strong statements, solidly proven. Most theorems are you don't have to do too much. If it's a weak theorem, very weak, we usually call it a lemma. We come and write lemma. A lemma is like a weak theorem. But if it's not a theorem, it's just something like that helps you. Let's say you've forgotten the name of the triangle inequality, but you just know the relationship, and you don't want to just blurt it out because we won't understand it. The triangle inequality is a statement that helps us prove bigger statements, right? So we can just call it. We call it corollary. You say corollary. Blah blah blah. You put your statement there. You will understand what it is. You will understand. Or if you don't want, okay, this is the best way of doing it. Write theorem, you claim your theorem there, then you proceed. But again, one thing is you must be cautious is never prevent a theorem of claim. If you come and say claim, this and this relate to each other. If you say claim, it means you want to prove that theorem. So never say claim. If you say claim, you will want to see how exactly you verify. So your wording is important. So if it's a theorem you're using to solve the problem statement, just say theorem, this is lemma, this is corollary, this is. Okay, if you don't know where to use corollary or lemma, just use theorem everywhere. If you don't know how to use those three, you can just say, since we know that, you can just say, since we know that, and then you put the theorem down there. Since we know that, and you assume that we know it because it's a theorem, we should be knowing it. So that's a safe way of putting it. Yeah. The method. Yep. Yes. Let's assume me and so supposing me and why am I right? Then if third party why is zero? Because it's wrong, it's wrong. So you think apart from what you think I'm not testing why I am right. I'm just saying I'm right, what am I thinking is wrong? And then I say, okay, if I'm thinking is wrong, means I'm right. And because I am right, it must be is wrong. Yeah, and because it must be that it's wrong, means it's wrong. Yeah. So you see how it's kind of so that is we call it pathology. So if you have the problem statement and you assume that this and this is true, and then you walk back to the question, if everything fits in well, how do you know that fits in well? If there's a double implication, if right implies left both ways and left implies right, then we say, no matter what we do, this will always work. But if it's just one-way implication, it could be that the forward direction is right, or the backward is right. So it's a tricky thing. It's very tricky to know when to use that. Now that we just jump into the game of logic, which is a dangerous thing. The minute you make a wrong argument the whole time. So you want to verify that most of the time you want to see when I work backwards, what does it tell me? So that I can telling you. So, but then they perfectly imply each other. That the backward method seems to imply the forward. Then you can just present. Any other question? Yeah. That's fine. Mm-hmm. Yeah. Mm-hmm. I think I understand what you're saying. So there are statements, there are those that are strong and there are those that are weak. For example, I can have a very strict and strong statement, similarity. And I can have a weak statement, congruence. Congruence. Like what we did yesterday in combinatorics, I can have a strong statement, exactly. And I can have a weak statement, at least. I can have another strong statement, double implication, another weak statement, quad implication. So if I say, let's say I had, this is what I had, A implies B, both way. If this is what I had, and then I forgot and I put A implies B just one way, we can pardon you for this because A implies B both way is the same as A implies B, and also the same as B implies A. So the weaker. Yeah. Okay, yeah. But then the danger here is supposing it was only one way, and then you come and present it as both way. Now that is just downright wrong. So you get no marks. If the implication is both is one way, and then you present, you get no marks. Yeah. Similarity. So again, it mostly depends. I know that if two triangles are similar, it means they are congruent, right? So that can be pardoned most of the time. If you say congruence other than similarity, it might be pardoned some of the time, some, not all the time. But then if you try presenting congruence as similarity, it will be very wrong because this is a much stronger requirement. So it will be too out of place to make such a claim. Have I addressed your question? Okay. All right. Yeah. Yeah. So, any other question? Okay, so have an done modulo, I think. Yeah, wonderful. 01. 01. So like maybe by concept. Yeah. The next one. Okay. Let me just. How many of you know what the in-center is? I want to know what the in-center is. In-center of the puzzle. Nice. So if I have a triangle, so if I have a triangle, then I have a circle inside that triangle, the Jones is telling me is that that is the incenter, and that's true. So the incenter, so it is the point of, or is the center of an inscribed circle, but it's also the point of concurrency of the angle bisectors. If I draw the angle bisectors, the incenter is the point of concurrency of those angle bisectors. Yeah. What's the orthocenter? Orthocenter. What's the orthocenter? You can come on. Marvin. Okay. Orthocenter is when you drop right angles to the different sides of the circle, the point of concurrency of those lines. So if I were to drop a right angle here, this is 90 degrees, and then I drop a right angle from, so I have A, B, C. If I drop a right angle from A to BC, and then I drop a line from B to AC, let's say this is the right angle, then I extend it here, and then I drop a right angle from a C to AB. If I drop a right angle from C to AB, they're going to meet at a point, and that point is going to be my orthocenter. Let me see, it's actually the symbol. The symbol is an H. That's going to be my orthocenter. So by dropping the perpendiculars to the different sides, I get the so-called orthocenter. That's the incenter, that's the orthocenter. How about the Alvin? So it will come and bisect the sides, and I keep bisecting the sides. The limit is a point here. So perpendicular bisectors of the sides, the limit is a point here that we're going to call the circumcenter. How about the centroid? The centroid. Come again. So if I draw median, so I draw median from vertex A to the bisector, the center, the midpoint of BC. I do the same from this other side. This is the center, so I draw that here. And I also do the same for C to AB. They'll meet at a point. Let's call it G. That will be our centroid. Yeah. So that's the centroid. How about, let me look for another. The circumcenter. Okay, yeah, we have the circumcenter. X center. What is the X center? Yeah, this is not. Yeah. Yeah. Yes. Could be wrong, but I don't. I'm not following that median. Okay, what does the median? Yeah.
What does it mean by median?
Yeah.
Maybe you can explain.
That's what I have. I have a trivium and a median. Trivium is any line joining a vertex to the right. A median is a line from a vertex to the midpoint. There's something interesting I've forgotten here. There's the x center, something the x center. So if I have a triangle, and then I bisect, let's say I have a triangle ABC, and I bisect the external angle ABC, this external angle. So I do that. I also bisect the external angle ACB, this angle here. They'll meet at a point. And if I were to draw, okay, if I were to draw a circle from this point, touching tangent to side BC, I'll have it tangent to the other. So we call this the X circle. And before this point, the X center. There is a lemma with regards to this, but I've forgotten to remember it and let you know. But it's good to keep the X center in the X circle. Okay. And yeah, a few tips again for geometry. Two tips I could put there would be number one, keep it simple. Keep it simple. Most of the time, geometry problems are, as I said, on the easier task, easier. So if you take a rabbit hole and you go, there's a question I saw. Sometimes someone they had a simple problem, but then when they looked at it, the first thing that crossed their mind, the first thing that crossed their mind was Menelaus. I also noticed this problem with one, the very first point. He saw every time he saw an important problem, the first thing that crossed his mind was AMGM. The first thing that crossed his mind was AMGM. So what exactly is the problem with that? If you're looking at the problem, what is the problem? Because in this solution, you have the student thought of Menelaus and they spent their whole time. So they spent a lot of time just trying to hold Menelaus. In fact, the theorem that was used to solve it was something called Peter's theorem, which is a very easy relationship. But the only problem is every time you see a problem and then you always think of a given relationship, you will forget to pay attention to what you should be paying attention. So the first thing you always want to do is, what is the problem asking? After you know what the problem is asking, how can I solve this problem? What is the simplest way of solving this problem? Otherwise, you'll spend so many hours lost in something. Another thing you need to do in geometry is mind your drawing. There's a, I don't know if I have it in this book. There's a beautiful problem from the US Army where it was essentially people who cannot mind their drawing. So the problem had an easy case. The problem was simple, but also not so simple, because if you drew the wrong diagram, you couldn't complete. If you drew the right diagram, then the proof would be easy. The only problem is to correct. So this is the first diagram. If you read the question, the first diagram that will cross your mind would be this. I'll just draw the diagram. Example. This was the first diagram that almost everyone saw. This is the center O1, this is the center O2, O2. That looking at some point here, point H, which is the auto center of the second triangle. I also fell into the same rabbit hole. You have O3. So H will be the opposite of this triangle. And we have a point S, we have a point T. So it's an easy problem to solve if you know the axis. But the only issue is this wasn't the only case. Remember from our rules, make sure you've always checked all the cases. There was another special case to observe that meant the condition to be correct. And it looked like this. Looked like this. So we had this. We had this. And we had that. We had a third circle there. So even without reading the problem, you can start seeing how they relate to each other. It's O1, O2. Yeah. Here, O1 is the center of circle 1. O3 is the center of circle 3. And this is circle 2. This is center. Yeah. So this is a special case that the bigger majority did not notice. And while it makes sense, it looks very weird. So the majority of students who couldn't see this couldn't finish it. And that's why it was a very ugly problem. Many people didn't see the problem. So you always want to mind your drawing. If you don't mind it, it will be disastrous. Another reason why you want to mind your drawing is what we had talked about it is if you draw an accurate diagram, you will most likely use the thing you draw to prove what you're supposed to be proving. For example, if the problem statement asks me to show that a given pentagon is regular, I could draw a regular pentagon, right? I'm not sure about this, but I think there's an IMO problem. The first problem in the short list of some year 2020. I'm not sure. I think 2020, where we had a given pentagon. Project load. And so you're given some relationships between certain angles. If you make that the pentagon is regular, you can easily know it. The only issue is the question is what you're supposed to be proving if the pentagon is regular. So your proof has been based on assuming that the pentagon is regular. So essentially, you're just proving anything. You're just assuming the distribution holds, and then work with that to go on a circle to go back to the distribution. So that's the danger of not being careful with the diagram. So if I have, let's say, a pentagon here, so I want to draw, but then I also want to deliberately draw a pentagon that is wrong. Why? Because if I draw a pentagon that is wrong, I can better see differences between the angles and see differences. A simple example can relate to where we had a parallel. And so we were trying to show that this line, that's true. Let's go to this. So we are trying to show that if you have a parallelogram, and this is the center of the parallelogram, I, A, B, you're trying to show that A, I, B is a straight line. At points A, point I, and point B are collinear. One mistake I could make is I could draw this as a straight line. Then after I draw it as a straight line, I'll just say, I'll use that in my proof. If I draw it as a straight line, it will seem so evident. And then I'll say that I'll use that in my statement, which would be a mistake because now I'm using the result. So that's why it's advisable. I do this and do a wrong line, and then so that I can see the difference. And most times when you get such problems, they'll always ask you, show that the sum of these two angles is equal to 180 degrees. There are many such problems that are going to be asked. And if you draw a straight line, you'll be tempted to claim it is 180. But if you draw a line that is then every time you look at the diagram, you always remember what it looks like. So keep it simple and mind your any questions on geometry. Next, I have to mention a few I want to mention the form of a point and radical. Oh, the lemma. The lemma insert. So, any question before we move? Any question before we move? No question? Okay, so that's it. The next, we're going to do some lemmas here. Because we have a lemma, a weak theorem, a weak form of theorem. A lemma is a weak theorem. So I have a circle. Yeah, it's not a good circle, but circle. I have that. And then I have another circle. Okay. It passes through this point. I have a triangle. A, B, C. So let's construct the incenter of this circle. Let's construct the incenter. So I have an incenter I in there. Well, yeah, let's just call it I. Incenter I. Let's draw a line from that. So here's a beautiful result. If I draw a straight line there through the incenter, it will come meet this circle at some point. So this is a circle that passes through point B and C. And also passes through the incenter, the X center here. So how do I determine the X center? We know that the X center is if I bisect these angles, I'll get the X center. And I also know how to find the incenter. So I can find the incenter, I can find the X center. If I draw a circle passing through B, IA, and C, where IA is the X center opposite point A. If it was opposite point B, we'd call it IB. which is opposite from C, we call it IC. Okay. So I have the in center and I have the X center. If I draw a straight line between those 2 points, I'll get a beautiful result. Okay, let me try. Let me just let me write. I'll call this point L, and I'll mention what I mean, why that should be important to us. Okay. I've forgotten something. I've made a mistake. If I draw this circle, between sorry, I have to draw this circle. If I draw the circle passing through B and C and the in center, it will also pass through the. Sorry, if I draw the circle passing through B and C and the in center, it will pass through the X center. And if I draw one passing through B, C, and the X center, it will also pass through the in center. So if you have a compass, you can do later on, you can try showing that is going to always happen. So that's a very interesting result that we achieved through construction. But the circle passing through points B, C, and the in center also passes through the X center. And in fact, if you don't want to construct the X center through the angles, you just need to draw that circle and then draw a line A through the in center. It will also pass. Where it's going to intersect with the circumference of this circle, that is going to be X center. That's going to be X center. Now, let me see. For the importance to us, let me write something. Yeah. Yeah, problem with the whiteboard. Let me just go out. Yeah. So construct the in center I and the X center IA. You can see clearly from the back. Can you see clearly? Okay. L is the midpoint and I is more. IC, IAB, IAB are concyclic with L as the center. L as the center. When I put the bar there, I just mean a line IIA. That's the diameter of the circle. This is an important and very interesting lemma to keep in mind. That, okay, the first part of the lemma which I have written is that we can only, if we move the circle through B and the I center, it will always pass through the X center, IA. Or we can just say, that if you draw a circle through BC and the X center, it will pass through the in center. And after that happens, so if we needed to find the X center, and we didn't know these angles, the angle, we didn't know the angle, the external angle ABC, so we can't bisect them because we don't know them. The way we can find the X center is just saying, let's draw a circle, BC and the in center. Let's find the in center. Draw that circle, and then draw a line AI and extend it. Where AI meets the circle, this circle, let me call it later. Where AI meets the circle again, that is going to be our X center. And if you have the X center and you have the in center, IIA, the place where the circumcircle of ABC, let's call it gamma, the place where circumcircle of gamma meets this other circle omega, they're going to meet at 2 points, which is B and C, actually. And then, not only that, the line IA is going to cross the circumcircle at some point L, and that L will be the center of circle omega. And circle omega will pass 2 points IA, B, I, and B, I, and C. Yeah. So one thing you'll notice is we are very obsessed. We are really, really obsessed with this whole idea of concyclic. The whole idea of concyclic. The reason we obsessed with concyclic is every time you can draw a circle, you can relate many angles to the circle. You can get many circles. And that's when you're going to just look at some of the things you can do every time you get a circle. That way we can, to some degree, appreciate the beauty of a circle. So one of the things you always want to try doing is you ask, can I show that some points are concyclic? But if I can show that, I have a very good. Let me present now. Yeah. So, anyone still writing? Can I move? Can I continue? So I'm going to present another lemma. Where did I get this? I got it from the short list of the IMO 2018. You can go take your time and try finding the short list of IMO 2018. I don't think I should present the proof of the lemma. It's a very simple lemma, but it's very heavy. This was the second lemma is this. The lemma is this. I have a circle. I have a circle. And I have AB. P, X, Y. I have that. So Supposing I had Cx is equals to Cy. Then if I have Cx is equals to Cy, so this lemma, so this lemma tells me something interesting. What is that? What's what the lemma says? You can take it down. Okay, the proof is rather simple. The strictness amount will change. Okay, the type of questions that you're going to be asked is to the first lemma. Why is that lemma important? Because you're going to be asked how to relate the various. Someone will come and ask you, how does the in-center relate? What's the distance between? How does the x-center relate to the central? How does central relate to the auto-center? You will also be asked what is the ratio between the distance from auto-center to central? Now, central x-center. So every single time you get a tool that can help you relate the center. Very good tool. Because the proof of this is quite simple, let's just go through it. I can also use this proof to try showing how to structure your using. Okay, I need to number them. Also, if you're going to present more than one lemma in your solution, be kind enough and number them. We can say proof. So for illustration, I'm going to drag a diagram up. We will be looking at the proof and also looking at the diagram. So supposing I had this diagram, a circle. I have x, y, z, this of which. Yeah, I have C A point x, y, x, y, and then the other opposite side should be b. Then I have that. So I'll write the proof on this other side so that you see the difference. Now I can present both the diagram after. So in the proof I put there, I presented both the diagram and then the solution underneath. So I can do that, but the diagram is not important. And you'll see in the argument how I don't infer the diagram. You can put it for illustration or maybe to guide you, but always notice that you must not assume that the examiner will look at the diagram. It's not of interest. So you can say proof of lemma 2. Okay. So the proof is rather simple. Draw a point. You can say draw what cy prime is equals to cy, cy prime is equals to cy on the opposite side of CA, on opposite side of CA. Okay, let's do that. So instead of assuming that I look at the diagram, I'm saying I'm giving statements of how I got whereas I'm highlighting what segments did I relate to which other segment. So if I draw cy prime is equal to cy, okay, so I have this answer. So cy prime is equal to cy on the opposite side of CA. So cy prime is equal to cy. I have that. Y prime is here. Okay. In fact, let me use a different color for. Let me use a different color for the proof. I have C Y prime on there. Okay, on the opposite side of CA. So then the next instruction is that I give is draw Y prime D through X to a circle. Oh. Trouble. Okay, let's finish this. Then we go for T. Starting between you and your T break. Draw Y prime D through X to the circle. The circle. So Y prime D through X to the circle. So draw Y prime D through X and to the circle. So that tells me that I have Y prime D that goes through X to the circle. That's Y prime D. The next piece of instruction I give, since triangle XYC is isosceles, okay, so I've made my highlights and then I'm going to say since triangle XYD is isosceles, XYD, so I have X, Y, and D is isosceles. Okay. Sorry, triangle XYC. Yes, I don't know I'm claiming XYD. How did I know? This triangle XYC is isosceles, XYC. So XYC is isosceles because we have XC is equals to YC is isosceles. And triangle XYC and triangle XYC is what's that notation? Is it similarity? Similar to triangle ABX. ABX. With similarity or congruence? I think it should be congruence. It's congruent to ABS. So is that the right notation? I think is a problem to the top one. With angle BAX. Okay, yeah, with angle BAX is equals to angle CYX. It's okay, angle BAX, angle BAX is equal to CYX, okay? They're equal because it's a circle. Chord BC subtends this angle, and chord BC subtends that angle. I don't need to mention it. You can easily see that. And you can also see chord AY subtends this angle, which is equal to this. And so it remains that we are congruent. The two triangles are congruent. ABX and CY. It implies, okay, let me see. This, okay, this implies AB is equals to BX. It implies this is AB is equals to BX because I find I find this angle here is equal to this angle because it's isosceles, which I mentioned here, XY is isosceles. But then it's also equal to this angle. But then we also know that this angle, I don't know how to call it, vertically opposite. Yes. So this is vertically opposite angle. So we have this angle is equal to that, equal to that, equal to that. So AB is equal to BF. IE triangle ABX is also isosceles. Triangle ABX is also isosceles. What implies AB equals to BX, i.e. triangle ABX is also isosceles. I hope are we together with everyone? From we say also give another statement. Also, since YC arc YC is equals to arc Y prime, sorry, not arc YC is equals to Y prime C. Also, since YC is equals to Y prime C, so notice when you created Y prime, you mentioned what you created. Draw a chord CY prime is equal to CY on the opposite side of CA. So CY prime should be equal to CY, so that's also equal. So we have that. Since YC is equal to Y prime C, and it's a circle, we will have that this would imply arc YC is equal to arc Y prime C. Yes. What this arc is equal to. So essentially, if you go back to the lemma, let's just look at the lemma first. If we go back to the solution, we are trying to show that as long as CX is equal to CY, we'll have that arc AB plus arc YC is always equal to arc BC. And how we want to prove that is by showing that arc CY is equal to arc CY prime, and then we make an analogous argument to show that BY prime is equal to arc AB. So if you can show that arc AB is equal to BY prime, we are essentially done. So I can say that it services, I can just write, not write too much. I can just say the services to show that BY prime is equal to AB. So BY prime is here. The services to show that BY prime is equal to AB. If I can show that BY prime is equal to AB, I would be done. If I can show that that is equal. Again, when drawing the diagram, we should not do this. If you do that, you will, at some point, you're going to forget. And so you're going to think that this is equal to this. Yes, that is the case. That is the answer. They're equal. But the question is, can you show that they are equal? So if you just come and draw the diagram and you put it like that and you forget, you're going to say that since by equals to AB, and you're going to assume the result, which you don't want to do. So it's actually to show that by prime is equals to AB. IE, actually, in IE, show that. I'll leave you guys to finish this. IE, show that triangle B, X, Y prime is isosceles. Again, I need you to notice a heuristic I've done here. I'm going from asking BY prime is equals to AB, and then I'll jump from that and replace that into so that triangle BXY prime is isosceles. Because if you show that it's isosceles, it would mean that if you show that it's isosceles such that this base angle is equal to this base angle, we have AB which is equal to BX is also equal to BY prime. Yeah. So I'll leave that for you to finish the proof for this. Yeah. There is a paper I've written here on one thing I came across in solving this problem was relate as many angles as you can, and you will see this result. And in fact, the diagram I drew, let me just draw the entire diagram of what I did. So most of the time, so this is the diagram I've drawn. I had that. I call this some angle A, call this E. I also had this. Call this angle B. Call this B, call this C. I call this, I had this. Call this B. Call this A. I had D here, I had F here. I had B plus F. B plus F there. I had F here, I had E here, I had B, I had C, I had A, I had E. I had A plus E, which is equal to A plus E here. So I also had that yeah, I had here it's also B plus C. I had this angle. What is it? Yeah, I had this angle to be B plus C as well. And so it was a very chaotic mess. In fact, the so okay, how I came to how I came to the proof I need to relate this. What I did is I worked backwards. This started working with the angles, putting the angles everywhere I can, and trying to see does this angle tell me something about whatever we're working with. Then after seeing the angles, I come and write like. One thing important I want you to look at is my diagram is very chaotic, it's very messy, it has many letters. Most likely the diagram will be this messy, if not messier. But then, in no part in my proof have I've not written too much. I've not come and put the A's and the E, B plus F. You can't see them anywhere here. So you also want to happen that. If I start putting, if I start defining, let A be this angle, B be this angle, C is equal to this angle. Two questions. One, is it useful to so you want to ask? Two, how does it affect my you just want to work to do angle chasing. The tip in proving this related to you will see how the angles relate to each other and which ones are the same. Then after that, you come and present an argument. So you say what you've done in the diagram. Don't assume you do it. So I can say, draw a chord this on the opposite side of CF. Draw this circle. Okay, we've done the drawing. We've done the highlighting of the relationship. Okay. since this one is an XYC is isosceles, it tells us that these ones hold. And also since this, it tells us that this. And so the problem that remains is showing this. And then with this, we can do more angle checking here and relate more triangle. And you can show that BXY is in fact isosceles. And AB, arc AB is equal to arc B1. Yeah. So what I wanted to highlight is the difference between your working and your proof. Although I will advise, if possible, you submit your rough record, you submit the rough record, so that if you have a problem in your answer, you can see what you want. And so it means in your rough record, you just want to leave it here. You want to come up with a small rough argument. You want to come with a small rough argument for the diagram, so that even if you've written something unclear here, they can come see what exactly for you trying to imply. When you say yeah. So that's not okay, don't you tell me when team break comes, so I don't get too much of your time. Yeah. So your future point challenge in your study IMO, the shortlist of the IMO 2018, problem G1. It is solved entirely using this lemma. IMO 2018 problem G1. Solved entirely using this. It's a very strong lemma, it's a very complex. It looks humble, but it's no, this is from the shortlist. No, the compendium ends in 2011. Yeah. So the shortlist yearly. So yes. So challenge yourself with problem G1. The simple thing. Just this is the one. Yeah. Okay. If you have multiple. Yeah. But this is our problem. Yeah. You. Yeah. No, I haven't. Not for 2019. I know. And I guess I sent them. Or they can Google. So you can get it. IMO. So check question G1 on the IMO. The first problem is the only apply okay. So let me mention okay. Let me you have many problems and I don't know when you finish all of them. So let me look here. Let me just mention radical axis, what radical axis, and what a power point is, what power so let's start with the power point theory. Currently, the whiteboard doesn't want us to continue. Power point theory. You've seen variants of them. Again, the challenge in form of point theorem, you have a circle, you have a line, you have another line. You have P, A, B, C, D. You have that. Let me close it and open it again. Yeah. So we go through power point theorem, we just highlight it. Then we highlight power over, okay, power point. Radical axis. We highlight the radical axis and highlight the radical center. What they mean. And give two lemmas with regards to those. There are problems I have now which needs the lemmas we mentioned here. So power point theorem. We have this. Then we say that PB all over PD, which PB over PD is equals to PC all over PA. Or we can say, we can just cross multiply PB by PA is equals to PC, PD by PC. That's power point theorem. PB over PD is equals to PC over PA. So this over this is equals to lower part of the So PB times PA is equal to PB times PC. That's one variant of the power point theorem. We can also have this. I've had this go by many names. I don't know, the intersector theorem. I'm not sure, but there's another name I've had for this. We have this. We have that. ACBD. We have ACBD. And we have a center P, a point P. So power point, we have considering the power of some point P. We will show how we get the power point. But essentially, the power point tells us that PB, this distance PB, all over the distance PD, is equals to PA over PC. PB over PD is equals to P over PC. Yeah. Or we can cross multiply PB times PC. PB times PC is equals to PA times PB. Okay, so that's of a point. Copy it and then you can move. So, okay, so this is the question someone might ask. So what exactly is the power of a point? I know we are making relationships here, but what is the power? So we're going to come and draw this and write PowerPoint power of a point. So supposing we have a circle omega, and it had a center O, and there's a point P. It could be inside the circle, it could be outside the circle. And so, power point basically, the power of any given circle is so supposing I have this line here. Evaluated by the line OP, I square that distance, and then I minus R squared. Okay, OP squared minus R squared. And how exactly do we find this minus R squared? How we find it is Pythagoras theorem. We come and say, draw a tangent from here to the circle. You draw a tangent, and here you have R 90 degrees, we have R here, and this is OP. And then we have, let's say, K, PK. And so, the power of the point with respect to the circle is just this distance, is just the square of the distance PK. It's essentially these two distances, P prime. So it's PK times PK prime. But how do you get PK times PK prime? We have that PK is equals to PK prime because they're both tangents to the circle. This is R. Let it load. So we have that PK is equals to PK prime. So essentially, we have PK squared. And when you have PK squared, by Pythagoras theorem, PK squared is equals to OP squared minus R squared. And that is the power of a given point to a circle. Yes. It's just the distance. It's just the product of the distance to the tangents. So PK times PK prime, which is equals to PK squared, which is OP squared minus R squared. And so, why should this be important? Because if we have OP minus R squared, now we don't need to know what PK is, the distance of the tangent. You only have to consider, do we have the center of the circle, and do you have the point P? Because if we have the circle, a circle is defined by the radius of the circle and the position of the center. So if you have the position of the center and the radius, and you also have a given random point, anywhere the point can be, we can always find the power of that point. So this is something to keep in mind for finding the power of the point. Okay, the notation I see being used is power with respect to circle omega. We call this circle omega. Power with respect to circle omega of a given point P is equals to OP squared minus R squared, where O is the center of the circle, R is the radius of the circle, and P is that point. Okay, it's tea break. So, yeah, we come back. Any questions before we get back? Any questions before we get back? Okay, no questions? Okay. I don't know what you'll do because they are.